Take a look at this question. And the number of cars arriving at a road junction, a 5-minute interval, recorded for 100 days. Mentions it's around the same time, so maybe consistency with when we record them, and the results are given below. So let's just zoom in a little bit. So for a 5-minute period, 0 cars arrived 12 times. And remember, we recorded 100 times. Okay, so these could be maybe 100 different days, or maybe 50 different days and 2 5-minute time periods between 12 and 1. Notice this, 11 cars arrived during a 5-minute period. That was quite rare, it occurred just once. And notice that these are, I suppose these are discrete values, aren't they? The number of cars can only be discrete data. So this is quite interesting that we have discrete data. So maybe it's no surprise that it's asking us to think about whether the data set can be modelled with a Poisson distribution. So let's get into answering the questions now. So let's look at A first. So explain the conditions under which the Poisson might be a good model. So let's have a little look here. So notice x, the variable we're measuring. X in our case, of course, x equals the number of cars arriving in 5 minutes. Okay, so x is the number of cars arriving in that 5-minute period at the junction. And so let's see if our situation matches the conditions for a Poisson to be a good model. So x counts the number of occurrences, or the number of cars of an event, in a given interval. The interval may have dimensions of time or space, well, per 5-minute time period, so that seems to be good. An average rate of occurrence in a given time interval is given. Well, we could hopefully work out the average rate of cars arriving in 5 minutes. So it's not given, but we should be able to work that out given the data. And the occurrences in a time interval are independent. Okay, so each car that arrives, the arrival of that car is independent from the arrival of another car. Okay, we might debate that in a moment. And occurrences cannot occur at the same time. Well, of course, each arrival is for a different car, right? So that a car can't be counted twice, right? But this is interesting, isn't it? The occurrences are independent. Now that, I suppose, is the only thing that might fall down in this case. It's worth mentioning, what if here's a particular road junction that we're measuring? So if we're measuring the cars arriving at this junction from this direction, what if there was some kind of road blockage here? And there was a set of traffic lights maybe here. So possibly there might be a backlog of cars here waiting at the traffic lights, and then when they go green you might actually get a whole bunch of cars arriving at the junction at the same time. And it wasn't independent events because they were all held at the same time here. So possibly this idea of independence might not hold in certain situations. But as we've managed to tick this, and maybe not that, it's probably enough. There are enough reasons there for it to be modelled by a Poisson. Now let's go back to the question here. And we go back to B, calculate the mean number of cars arriving at the junction. So basically we've got to work out the mean of this frequency table. Okay, remember, let's think about how to interpret it. We know there are 100 occurrences. The sum of frequencies here is 100. So there's 100 times we record the number of cars. And this here represents 30 cars arriving at the junction. This represents 40 cars. So what we need for the mean, of course, is the total cars divided by total frequency. And this is sigma x times by f over sigma f. And if you go back to your table of values, this is variable x and this is f here. Now we don't need to do anything much more than that except get our data here into our TI-Nspire and let the calculator do the work for us. So let's click out of there. Let's get this guy here. And I've already put a spreadsheet in here. I'm going to call this x and this f here. And the x is 0, I'll do up to 11. And then the frequencies all in 12, 10, 19, 17, 10, 8, 7, 5, 5, 3, 3, 1. Just check that everything's full. Yep, perfect. And then in the first free space here, let's make this quite big. Menu, statistics, stat calc. Of course, it's one variable statistic. The variable is x, the number of cars. We've got one list. The x list is variable x, and the frequency list is f. Okay, and there's x bar. So x bar is 3.64. You can just check that we have, there we go, look. We've got the number of days we recorded this, or the number of times we recorded the cars at the junction was 100, so that all ties in together. And so we've got 3.64 for x bar. So let's write that down. Okay, so x bar, oh, I'm just going to back up, there we go. X bar equals 3.64. Now that's going to form the major part now of our chi-squared goodness of fit test. So the null and the alternate hypothesis is that x can be modelled. X follows a Poisson with a mean of 3.64, and x cannot be followed, modelled by a Poisson 3.64. You could write this in words, so I'm just going to write it quickly with symbols like this. And now we've got to work out the expected values. So if this was a good model for the Poisson, we need to work out what we'd expect the number of occurrences to be. And so this is where we can go back to our spreadsheet and just use the power of Poisson PDF. So let's go back to calculator here, and we're going to now go and just adjust these a little bit, because here I'm going to put O now, and these are going to be expected, and the formula in here is going to be equals menu, statistics, distribution, and we're going to do a Poisson PDF. So Poisson PDF, lambda is 3.64, the average number of cars every 5 minutes, and the x values are just going to be taken from the variable x column, enter, and it is a variable reference, okay, and here we are. Now don't forget, we've actually got to add on a little bit extra here, because these are the probabilities of having 0 cars, right? And the probability of having 1 car, the probability of having 2 cars. So all the way down to here, the probability of having 11 cars, it looks like 9.7, but it's actually 9.7 times 10 to the negative 4. So in this formula, of course, we have 100 occurrences. So we need to multiply these probabilities by 100, right? So I'm just going to go back in here to the formula. I'm going to double click on it, and I'm going to put 100 times. So I'm not going to create an extra column. I'm going to overwrite, and there we have it. So we have the observed. Oh, let me just cancel that. We have the observed, and we have the expected here. The observed and the expected. Now there's a few little adjustments we need to make for this data here before we can do the chi-squared goodness of fit test. So we observe 12 times that no cars hit the junction. We expect 2.6, so that seems to be quite a long way off. We observe 10, we expect 9.6. We observe 19, we expect 17. These are quite close then, these sections here. But then going down here, it seems to be, we observe 10, we expect 19 cars, if the Poisson is a good model. And as we go down, you can see that it's getting a little bit further and further and further away. Now we could go ahead and go do the chi-squared goodness of fit test using the calculator test mode there, but there's 1 or 2 adjustments we need to make. Any chi-squared test, when you look at the expected values, if you have any expected values less than 5, the test isn't as valid as it could be. So one thing we could do here is we could group together any expected values less than 5. So I'm looking at all of these here, where we're thinking, well, actually, 7 or more we're going to put together as 1. So this is going to be, we're going to put 7 plus here. I'm wondering if my calculator will accept that. Okay, so here we're going to put, let's say 7. So, okay, it won't let me actually label it here, it will only let me put in a number, but I'm just going to add all these together from 7, 8, 9, 10, 11 down, and let's just make that happen in this little column here. So 5, 10, 13, 16, 17. So I'm going to put 17 here. I'm going to delete this, delete this, delete this, delete this. And then, of course, I should be adding together all of these numbers. So I need to add together all of these numbers and put the expected frequency for the times that we have 7 or more cars. All right. So maybe I'll just go back to this table of values and we're just going to write down what we found out there. If I just zoom in a little bit. So if I come across to a new page now, we've got the observed and we've got the expected. Just do a quick table. And this is the number of cars. 0, 1, 2, 3, 4, 5, 6, 7 plus. And the observed and the expected we can get from our calculator again. Let's go back up. And you can see that actually we've got 2.6 here and 9.5 here. So we're actually going to combine the 0 and 1. So the observed is 22. And the expected, you can see it's this number plus this number. So I'm just going to copy and paste this. I'm going to copy and paste this. I'm going to put a little formula equals the number above plus the number above. And I've got 12.2. I'll round it to 3 sig fig. The numbers from 2 through to 6, I think, stand on their own. Remember, any expected frequency less than 5, the test is not as valid as it might be. And we can make a small adjustment to make it more valid. So let's have a little look. 2 here, we've got 19 is the observed. The expected is 17.4. And we'll just go down. 5 is 8, the expected is 13 point, that's actually 14.0, isn't it, to 3 sig fig, so let's get that organised. 6 and 8.48, and then 7 plus, 17 in this, and then all of the others added together. So I'll just do the same thing again. I'll put in a formula here, equals this number plus this number plus, just scroll down, I've got C8, I've got C9, C10 plus C11 plus C11 plus C12. I think that's it. Let's just go back to see what the number is. Of course, you can just type this out on your calculator regularly. I've got 7.62. Okay, so finally I've got all the information I need. I might just tidy this up and put another spreadsheet in actually. So if I go doc, insert a new problem, I'll get a spreadsheet in here. I'll put observed and expected. And now we're just going to transfer our numbers in from our table. So the observed is 22, 19, 17, 10, 8, 7, 17, and the expected all the way back to the top now. 12.2, 17.4, 21.1, 19.2, 14, 8.48 and 7.62. Phew, so that's quite a lot of work there. Now we're going to have to go and try and do our test now. So let's go back to our question. We need to do a chi-squared goodness of fit test at the 5% level of significance. Alright, and we're testing against the null hypothesis that the data does fit a Poisson, and the data doesn't fit a Poisson with this particular average number of cars. So let's go ahead and do the test now. Menu, statistics, stat test, chi-squared goodness of fit. The observed list is O for observed. The expected list is E. Now degrees of freedom. So degrees of freedom is usually 1, 2, 3, 4, 5, 6. You've got 7 categories, and then subtract 1 is 6. So usually 7 minus 1 equals 6 is the degrees of freedom. But in this case we also estimated the population mean, so that is another restriction. So in fact our case, the degrees of freedom is 6 minus 1 equals to 5. So we'll type in 5 and we'll press OK. So the chi-squared test value, and we'll go back here and write this down. So the degrees of freedom we said was 5. The chi-squared test statistic was equal to 27.6, and the p-value. Now the p-value is something incredibly small. It's 4.36 times 10 to the negative 5. So the conclusion is pretty apparent here. The p-value is really the probability that the null hypothesis is actually true, and this is such a tiny, tiny, tiny chance that we reject H0 as our p-value is less than the 5% we're testing at. And simply in words, we'll go right to the top here. The number of cars arriving at the junction cannot be modelled by a Poisson distribution with mean equal to 3.64. Now it's unlikely it's going to be modelled by a Poisson with any other mean, because this was the mean number of cars arriving, right? So even if we tried to change that lambda to 4 or 3, the Poisson still wouldn't be a good fit. So that's how to do a Poisson goodness of fit test. I hope that helps.